Good morning, everyone, and welcome to Petroleum Production Engineering. Before we begin, let me ask you a simple question. Is drilling a successful well enough to make an oil company profitable? Not necessarily. A well only creates value if it can produce oil or gas safely, efficiently, and economically over its lifetime. That is the role of petroleum production engineering. In this course, we will study the complete production system, from the reservoir to the surface facilities. You'll learn how fluids flow, why production declines, how to identify production problems, and how engineers improve well performance. By the end of the course, you should be able to evaluate a producing well and recommend practical solutions to optimize production. Let's begin by understanding the role and responsibilities of a petroleum production engineer. Before we discuss production engineering, I'd like to share this certificate with you. It represents a specialist training program completed with Dowell Schlumberger. One thing you'll discover in this industry is that your university degree is only the beginning. The oil and gas industry changes continuously with new technologies, software, equipment, and production methods. To remain valuable as an engineer, you must keep learning throughout your career. Companies invest heavily in training because well-informed engineers make better technical decisions, improve production, reduce costs, and enhance safety. My advice is simple: never stop learning. Every course, certification, field experience, and technical paper adds to your engineering knowledge and makes you a better production engineer. Throughout this course, I encourage you to build that mindset. Learn not just to pass the exam, but to become an engineer whom industry can trust. The primary role of a production engineer is to keep wells producing as close as possible to their optimum production rate. But before we can improve a well, we first need to understand how it is currently performing. To do that, we must answer two fundamental questions. First, what can this well actually produce? Second, what is preventing it from reaching that potential? Answering these questions requires a thorough understanding of the reservoir and the production system. We need information about the reservoir properties, fluid characteristics, reservoir pressure and depletion, fluid saturations, relative permeability, any formation damage, and the efficiency of the lifting system. Each of these factors influences the well's performance. Once we understand the system, we can estimate the maximum obtainable production rate. However, this is not always the rate at which the well is allowed to produce. Production may also be limited by government regulations, facility capacity, market demand, or company operating policies. Taking these constraints into account gives us the maximum permissible production rate. Therefore, the job of a production engineer is not simply to increase production. It is to optimize production within both the technical and operational constraints of the field. Once we've determined that a well is producing below its optimum rate, the next step is to find out why. As production engineers, we should never assume the problem. Instead, we investigate it systematically using engineering principles and diagnostic tools. In general, production problems fall into four main categories. The first is reservoir problems, such as low permeability or declining reservoir pressure, which reduce the energy available to drive fluids toward the well. The second category is fluid problems. High oil viscosity, gas coming out of solution, or water encroachment can all make fluid flow more difficult and reduce production. The third category is well problems, often referred to as skin damage. Examples include clay swelling, emulsion blockage, water blocking, or poor perforation performance. These problems restrict flow near the wellbore and can significantly reduce well productivity. Finally, we have equipment problems, such as worn pumps, malfunctioning gas lift valves, or poorly designed tubing strings. Even if the reservoir and well are in good condition, inefficient equipment can still limit production. Identifying the correct cause is critical because the solution depends on the problem. For example, increasing pump capacity will not solve formation damage, and acidizing the formation will not help if the real issue is a worn-out pump. Therefore, production engineers rely on diagnostic techniques to identify the root cause before selecting the most appropriate remedial action. Let's look at an example of how production engineers solve a common problem. Suppose a well is completed in a low permeability reservoir. Even though there may be plenty of hydrocarbons in place, the formation does not allow fluids to flow easily toward the wellbore. One of the most effective solutions in this case is hydraulic fracturing, or HF. The objective of hydraulic fracturing is to increase well productivity by creating a highly conductive fracture that provides an easier flow path for reservoir fluids. From the radial inflow equation, we know that the production rate can be increased in several ways. First, hydraulic fracturing can increase the formation flow capacity, or KH, by connecting more of the reservoir to the well or by intersecting zones with higher permeability. Second, it can bypass near wellbore damage, reducing the skin factor and minimizing the additional pressure drop caused by formation damage. Finally, the fracture acts as an extension of the wellbore, increasing the effective wellbore radius. Instead of fluids flowing to the original wellbore radius, they flow to a much larger effective radius determined by the fracture length. This reduces flow resistance and increases production. As you'll see later in the course, hydraulic fracturing is one of many production optimization techniques. The choice of technique always depends on understanding the root cause of the production problem. To understand why hydraulic fracturing is so effective, we first need to understand where pressure losses occur as fluids flow toward the well. According to Darcy's law, the pressure gradient is directly proportional to the flow velocity. In simple terms, the faster the fluid moves, the greater the pressure loss required to move it. In a radial flow system, the production rate is the same at every radius, but the flow area becomes much smaller as the fluid approaches the wellbore. As a result, the fluid velocity increases dramatically near the wellbore. In fact, measurements show that the flow velocity at a typical 6-inch wellbore can be around 2,000 times greater than at the outer boundary of the drainage area. Consequently, the largest pressure drop occurs very close to the wellbore. This is exactly where hydraulic fracturing provides its greatest benefit. By creating a long, conductive fracture, the well behaves as if it has a much larger effective wellbore radius. Instead of all the fluid converging into a small 6-inch opening, it enters along the length of the fracture. This greatly reduces the flow velocity near the wellbore, minimizes pressure losses, and allows the well to produce at a higher rate. The key message is that hydraulic fracturing improves production not by creating more reservoir energy, but by reducing flow resistance where the pressure losses are greatest. That is why it is particularly effective in low permeability reservoirs. Let's apply what we've just learned to a practical example. Here we have data for an oil well, including the production rate, permeability, reservoir thickness, wellbore radius, drainage area, oil viscosity, and bottom hole pressure. Our objective is to calculate the pressure distribution in the reservoir and determine the pressure drop over different 1-foot intervals, starting from the wellbore and moving outward. Before we begin the calculations, I'd like you to predict where the largest pressure drop will occur. Will it be close to the wellbore or near the edge of the drainage area? Based on our discussion of Darcy's law, the answer should be near the wellbore. This is where the flow area is smallest, the fluid velocity is highest, and therefore the pressure gradient is greatest. As we work through the calculations, you'll see that the pressure drop between 0.25 and 1.25 feet is much greater than the pressure drop between 744 and 745 feet, even though both intervals are 1 foot long. This clearly demonstrates why the region near the wellbore has the greatest influence on well performance, and why treatments such as hydraulic fracturing can significantly improve production. Let's examine the results of the previous example. Notice what happens when the effective wellbore radius is increased from 6 inches to 100 feet. The flowing reservoir pressure increases from approximately 1861 psi to 2329 psi. This increase occurs because enlarging the effective wellbore radius reduces the pressure losses near the wellbore, where they are normally the greatest. In other words, the well can produce the same amount of fluid with much less pressure drawdown. Maintaining a higher flowing pressure has several important advantages. It allows the well to produce at higher rates, reduces stress on the reservoir, and helps delay production problems such as sand production, gas coning, and water coning. The key takeaway is that treatments like hydraulic fracturing do not increase the reservoir's energy. Instead, they improve the efficiency of fluid flow by reducing near wellbore pressure losses. This improves well performance and can extend the economic life of the reservoir. So far, we've seen how hydraulic fracturing improves production by reducing pressure losses near the wellbore. However, Not every reservoir responds in the same way. One of the most important factors controlling the success of a hydraulic fracturing treatment is permeability. In low permeability reservoirs, fluids experience high resistance as they flow through the rock. By creating a highly conductive fracture, we provide a much easier pathway for the fluids to reach the wellbore, significantly reducing pressure losses and increasing production. The reservoir permeability also influences the optimum fracture design. In general, lower permeability formations require longer fractures to effectively contact more of the reservoir, while higher permeability formations may achieve good performance with shorter fractures. To assist with fracture design, engineers use a parameter called the dimensionless fracture conductivity, or CD. This parameter compares the ability of the fracture to conduct fluids with the ability of the surrounding formation. It helps engineers determine the appropriate fracture length and conductivity to achieve the best production performance. In the following lectures, we'll see how this parameter is used to optimize hydraulic fracture design for different reservoir conditions. Let's work through another example to see how engineers use the dimensionless fracture conductivity in fracture design. In this example, the reservoir permeability, fracture width, fracture length, and target conductivity are given. Our objective is to determine the required fracture permeability. By substituting these values into the dimensionless fracture conductivity equation, we find that the required fracture permeability is approximately 1,600 Darcys. At first glance, this value may seem extremely high compared with the reservoir permeability of only 10 millidarcies. However, this is exactly what makes hydraulic fracturing effective. The fracture must be many thousands of times more conductive than the surrounding formation so that fluids preferentially flow through the fracture instead of the low permeability rock. This example highlights an important design principle. A successful hydraulic fracture is not just long, it must also be highly conductive. Both fracture geometry and fracture conductivity are essential for maximizing well productivity. So far, we've discussed how production engineers improve well performance by reducing flow resistance near the wellbore. However, before we can optimize production, we must understand a more fundamental question. What drives the oil and gas from the reservoir to the well? The answer lies in the reservoir drive mechanism. Every reservoir contains a source of energy that pushes hydrocarbons toward the producing well, but not all reservoirs behave the same way. The type of drive mechanism controls production rates, pressure decline, and ultimately the recovery factor. The main drive mechanisms are solution gas drive, gas cap drive, water drive, and compaction drive. Some reservoirs are dominated by a single mechanism, while others may have a combination of two or more. As shown in the figure, each drive mechanism has a different reservoir geometry and pressure behavior. On the right, notice how reservoir pressure declines over time. A solution gas drive reservoir loses pressure rapidly because there is little external support. In contrast, a water drive reservoir maintains pressure much better as water continuously replaces the produced fluids. Gas cap and compaction drives behave somewhere in between. Understanding the reservoir drive mechanism is essential because it influences every production decision we make. It helps us predict future production, select the most appropriate production strategy, and determine whether pressure support or enhanced recovery methods will be needed later in the field's life. Before attempting to optimize any well, a production engineer must first understand the source of the reservoir's energy. Without that understanding, it is impossible to develop an effective production strategy. Before we move on to the technical aspects of this course, I'd like you to think about the life of an oil or gas field. Like a human being, every field has a life cycle. It begins with discovery, grows through development, reaches peak production, gradually declines, and eventually reaches the end of its productive life. As production engineers, our responsibility is not simply to produce as much oil as possible, as quickly as possible. Our responsibility is to maximize the value of the asset throughout its entire life. Sometimes that means increasing production, but other times it means controlling production, maintaining reservoir pressure, extending field life, or reducing operating costs. When a field reaches maturity, our work does not end. We look for ways to revitalize wells through stimulation, workovers, artificial lift, or improved recovery methods. Even after hydrocarbon production is no longer economical, the infrastructure and reservoirs may still have value through applications such as carbon storage or geothermal energy. Finally, every engineer has an ethical responsibility. We must leave the field in a safe condition, protect the environment, and ensure that future generations are not burdened by today's operations. Success is not measured by how quickly we produce a reservoir, but by how responsibly we manage it from discovery to decommissioning. I want you to remember one message throughout this course. A great production engineer does not simply produce hydrocarbons. A great production engineer creates long-term value while protecting people, the environment, and the asset. This diagram summarizes the entire course. From now on, I want you to think of a producing well as one complete production system, not a collection of separate components. The journey of the hydrocarbons begins in the reservoir, where oil and gas flow through the porous rock toward the wellbore. They then travel through the completion, tubing, wellhead, flow lines, and finally reach the separator, where the fluids are processed. Notice that I divided the production system into 3 stages. The first is flow from the reservoir to the bottom hole, the second is flow from the bottom hole to the surface, and the third is flow from the wellhead to the separator and processing facilities. At every stage, pressure is lost because of flow resistance. These pressure losses determine how much the well can ultimately produce. Therefore, if production is below expectations, our job is to identify where the bottleneck exists, not simply assume the problem is in the reservoir or at the surface. Throughout this course, we'll learn how to evaluate each stage using tools such as inflow performance relationships, IPR, vertical lift performance, VLP, tubing performance, TP, choke performance, CP, and finally nodal analysis, which combines them into one integrated model. The key message is simple. A production system is only as strong as its weakest component. Improving one part of the system will have little benefit if another part remains the limiting factor. That is why production engineers always optimize the entire system, not individual components. Now that we've seen the components of the production system, let's examine how pressure changes as fluids travel from the reservoir to the storage tank. This pressure profile is one of the most important concepts in petroleum production engineering. The reservoir provides both the hydrocarbons and the energy required to move them toward the surface. However, as the fluids flow through the reservoir, enter the wellbore, travel up the tubing, pass through the wellhead and choke, and finally reach the separator and storage facilities, they experience a series of pressure losses. Notice that the pressure does not decrease uniformly. The largest pressure losses occur where the flow encounters the greatest resistance, such as near the wellbore and across the surface choke. Each component of the production system contributes to the total pressure drop. An important point to remember is that flow occurs because of a pressure difference. The greater the pressure gradient between the reservoir and the surface, the greater the driving force for fluid flow. However, increasing the production rate also increases frictional losses, resulting in larger pressure drops throughout the system. Therefore, the role of a production engineer is to manage these pressure losses and optimize the pressure profile so that the well produces safely, efficiently, and economically. Throughout this course, many of our calculations will focus on understanding and minimizing these pressure losses. So far, we've focused on a single well. In reality, however, an oil or gas field consists of many wells producing simultaneously. These wells are connected through a production network before the fluids reach the processing facilities. As shown in this diagram, the produced fluids first leave the wellhead and enter the production manifold, where the flow from multiple wells is collected and controlled. From there, the fluids are directed to a production separator, which separates oil, gas, and water. Test separators are also used to evaluate the performance of individual wells. After separation, the production is measured for production allocation, reservoir management, and commercial reporting before the fluids are sent to storage tanks, pipelines, or export facilities. The design of these surface flow lines is also important. Although we won't study pipeline design in detail, every production engineer should understand the basic principles. The pipe diameter must be selected carefully. If it is too small, the fluid velocity becomes high, increasing frictional pressure losses. If it is too large, the velocity may become too low, allowing liquids to accumulate and reducing flow efficiency. The pipe material and wall thickness are selected based on the expected pressure, temperature, and fluid properties to ensure safe operation. In addition, engineers try to design the production network with the shortest practical flow path and the fewest restrictions, since every valve, bend, fitting, and choke creates an additional pressure loss. The key message is that production optimization does not stop at the wellhead. A production engineer must optimize the entire system, from the reservoir to the surface facilities, ensuring that hydrocarbons are transported safely, efficiently, and with minimum pressure losses. Up to this point, We have discussed how fluids flow through the production system. Now we need to answer another important question. Does the fluid remain the same from the reservoir to the surface? The answer is no. As pressure and temperature change, the fluid itself changes. Let's follow the journey of a reservoir fluid. Deep in the reservoir, the pressure is very high, and the hydrocarbons usually exist as a single liquid phase because the pressure is above the bubble point pressure. At this stage, all the gas is dissolved in the oil, much like carbon dioxide dissolved in a sealed soft drink bottle. As the fluid enters the wellbore and flows toward the surface, the pressure continuously decreases. Eventually, it reaches the bubble point pressure, where the oil can no longer retain all the dissolved gas. Gas bubbles begin to form, and the fluid changes from a single-phase liquid to a two-phase mixture of oil and gas. As pressure continues to decline, more gas evolves, changing the fluid's density, viscosity, and flow characteristics. This concept is extremely important because the classification of hydrocarbon reservoirs is largely based on phase behavior. For example, black oil reservoirs, volatile oil reservoirs, gas condensate reservoirs, and dry gas reservoirs all behave differently as pressure and temperature change. Their production performance, recovery mechanisms, surface facilities, and even development strategies depend on how the fluids undergo these phase changes. Therefore, understanding phase behavior is essential not only for production engineering but also for reservoir engineering and surface facility design. Once the fluids reach the surface, they enter the separator, where pressure is reduced under controlled conditions. The separator allows the gas to separate from the liquid, producing separate streams of oil, gas, and, if present, water. These streams are then measured and sent for processing, storage, or export. The key message is this: pressure changes do not only drive fluid flow, they also change the fluid itself. As production engineers, we must understand both the movement of the fluid and its phase behavior, because together they determine well performance, equipment design, production strategy, and ultimately the economic success of the field. Before we move on to the next chapter, let's take a moment to summarize the key ideas we've learned. Throughout this chapter, we've seen that petroleum production engineering is much more than producing oil and gas. It is about maximizing value by ensuring hydrocarbons move safely, efficiently, and economically from the reservoir to the market. We followed the journey of the hydrocarbons, starting in the reservoir, flowing through the well, the production manifold, the separator, the measurement system, and finally to processing or export facilities. Every component in this chain influences the overall performance of the production system. We also learned that pressure is the driving force for production. As fluids move toward the surface, pressure continuously decreases, and every component introduces pressure losses. As production engineers, our responsibility is to identify where these losses occur and minimize them whenever possible. Another important concept is phase behavior. Reservoir fluids do not remain the same as they travel to the surface. As pressure and temperature change, oil and gas may separate into different phases. This behavior forms the basis for classifying reservoirs as black oil, volatile oil, gas condensate, or dry gas, and it strongly influences production performance and facility design. Finally, we discussed the complete life cycle of an oil field. Our responsibility is not simply to increase production, but to manage the asset wisely from discovery to decommissioning, while protecting people, the environment, and creating long-term value. If you remember one message from this chapter, let it be this: a production engineer does not optimize individual components. A production engineer optimizes the entire production system. Every decision should improve safety, reliability, efficiency, and economic performance. That systems thinking approach will guide everything we study in the chapters ahead.